Hello everyone, my name is Mark. Welcome to my MA261 Fall 2019 exam walkthrough video. So this is sort of the moment that we can apply everything that we have learned from previous videos into an exam copy, right? So pretty much every videos I have talked about how do you apply these solving steps to every type of problems, right? So I want you to look at the question types, and then by looking at the keywords, you can figure out the question type, and then in order to once you identify the type of questions, you can recall your solving steps on your exams, right? Because on every exam, you probably have about 5 to 6 minutes on average per question, so you don't have a lot of time and to solve each one. So you get the keywords, you get the question type, and you need to recall your solving step really quickly. So any missing informations, any key equations that you need to use to solve that problem. So with that said, let's go ahead and start the first question. So the first question, find the equation of the plane through the point 0, 1, 2 perpendicular to the planes given by plane 1 and plane 2. Okay, so this one is a little bit different, but I think everybody can agree that it has something to do with equations of the plane, right? So this is our first keywords, that has something about talking about planes, and then this will kind of allude you or hinting you about some problems related to lines and planes in 3D. So in this case, it's plane equations in 3D space. So in this case, we're asked for the plane perpendicular to two other planes. So the first step we're going to solve this type of problem is to find the normal vectors of the planes that we have already been provided, v1 and v2. So v1 is going to be the coefficients of the first plane, so that's going to be 1 minus 1, 2. And then v2 is going to be 3, 0, 2. So that's your first step. And then the second step is that once we have these two vectors, we're going to find the normal vector that is that by taking the cross product to find the normal vector. We call them the ABC for each perspective components. So this Vn is the vector perpendicular to V1 and V2, and it is also parallel to the intersecting line. This vector can be used to find the intersecting line of the two vectors as well, and we have already mentioned about that in my lines and planes in 3D videos. So we're not going to touch base on that. So we're going to take the cross product, but I'm not going to show you the professor, the I, J, K, and then your first vector, your second vector, that. I'm going to show you a new way. You can take it, you can use it or not. I think personally I prefer this method, and it saves me a bunch of hassle of doing a bunch of smaller determinant and have the making sure I always remember this negative sign in the middle. So I'm going to show you a new way. So Vn equals to V1 cross V2 equals to okay, what do we have? So 1 I hat, 1 negative 1 j hat, and then 2 k hat cross with 3 I hat plus 0 j hat plus 2 k hat. Okay, so that's all fine and dandy. So before I compute the cross product, I'm gonna always draw myself a little table. I'm just gonna follow it like this. So your first unit vector I, second unit vector j, and third vector k, and then repeat this for I and j for the first and second one. Okay, and I'm gonna draw a little sign like that. Draw a little arrow. I'm gonna call it plus. I'm gonna draw another arrow backwards called minus, and it has a minus notation. So what do I mean by that? So what we're gonna do is we're going to compute So I'm gonna start with this vector. So I'm gonna highlight it in red. So I'm gonna select this one. I'm going to let this unit vector cross product with this vector, and this vector. So let's start with a scalar. So we have 1 and 3. So 1 times 3, right? So we have these two dotted together. It's a bunch of smaller dot product, smaller cross products. So it's going to be times I hat times I hat. Okay. Plus, and then I'm going to move on to the second one. So 1 times 0. I hat that j hat, and then plus, and then move on to the third one, right? I hat I time 1 times 2 times I hat. Sorry, not these are not dots. These are crosses. Never mind. Cross product was k hat. So let's repeat this again. So we're going to have actually before I continue, I'm gonna go ahead and start writing some conclusions too. So I hope so let's start with equal to here. So this thing what we computed right here is gonna be equal to, because any vector cross product with itself is going to be equal to 0. So this thing will drop out because this part is 0, right? And then this drops out, so we're gonna have just 2. So we're gonna end up with 2 from here. So which unit vector hat we should be using? So this comes back to this table that I have drew right here. So because we have I cross with k, so we're going from I go to k, right? So we're going from right to left. So we're following this arrow. We're going to the next one. So I cross with j, we're going to get an I hat. Because we're going from right to left, we're going to have minus sign in front of it. So instead of so it's going to be j hat but minus 2. Okay, so let's repeat again for this vector, and then we're going to repeat the whole process. So I'm going to go ahead and remove this red box. So I'm going to times with the first component right here. Okay, so this component right here. So we're going to get -3, and then times j cross I, and then we're going to plus 0 dotted with j cross j, and then plus j plus j times j cross j, and then I'm gonna have -1 times 2, so -2 times j cross k, and I'm gonna have, and then I hope to start to get the gist of it. So I'm gonna speed through the last one. By the way, actually, it's going to evaluate the second line. Is so j and I, right? So we have j and I. So we're going from right to left. We arrive to the k, always the one next to it. So that's a k. So it's a, but it's we're going from right to left. It's a negative sign. So we're gonna end up with a negative k. So it's -3 k. So we're gonna have plus 3k for this term. And then we're gonna have 0. So this drops out. So we're not gonna worry about that. I mean, j cross j is 0 anyway. We're also going to have j cross k. So j k I. So it's from left to right. So we're following the positive sign. So we're going to arrive to the I hat, and it's a positive sign. So we're going to have -2 positive I hat. Okay, I hope you get the gist of it. So now let's go ahead and start doing the last part. So it's the k, 2k times the rest of it. So it's going to be 6, 8. So k cross I, ki, we're going to have it right. J is a positive j hat, and then plus, again, it's 2 times 0 is 0, so we're not gonna worry about it, and it's gonna be kj, right? So kj -1, right? Right to left, so times with -1, a negative I hat, and then plus 0, right? K times k cross k is 0, so we're gonna end up with plus 6j coming from here. So what we're gonna end up with is gonna be -2i hat plus 4j hat plus 3k hat. Okay, so that's how you do it. So finally, we can utilize we have the normal vector, and we can apply the plane equation, which is demonstrated as follows. So the ABC is going to come from the normal vector components, A, B, C, and then x0, y0, z0 is going to be coming from the point of interest right here. So it's going to be 0, 1, 2. So plugging all of this in, we're going to end up -2x minus 0 plus 4 times y minus 1 plus 3z minus 2 equals to 0. Okay, and then 2x minus 2x minus plus 4y plus 3z equals to 10. So we're gonna flip everything. We can flip everything. We're gonna get plus 2x minus 4y minus 3d equals to minus 10. Oh, come on, let me zoom. Let me drag things around. Properties. So, and I think this should be the correct answer for question number 1. So that is answer choice B. Okay, so second question. Identify the surface through completing the square. So, right, so the key words are identify the surface as well as these answer choices, right? If you look at the answer choices, you can see that they have the name of the quadric surfaces that we have learned about. So the keywords are identify surfaces and the name of the surfaces themselves in the answer choices. So therefore, this is a surface identification problem. So first step, as the question has alluded to, is we're going to obtain the standard form of the surface equation. Okay, I do not recommend people hardwiring the equations to the shape of the surface, because you cannot use those equations to relate them to the names unless they are in the standard form. So in this case, they are not in the standard form, so we have to complete the square to get to the standard form. So we have 2x squared minus 4x, right, moving things to the left hand side, minus 2y squared plus 3z squared equals to 0. And then we're going to have x squared minus 2x minus y squared plus 3 over 2 z squared equals to 0, right? We're dividing everything by 2. So as you can see here, if we multiply, add both sides by 1, right? So x squared minus 2x plus 1 minus y squared plus 3 over 2 z squared equals to 1. We're going to end up with x minus 1 squared minus y squared plus 3 over 2 z squared equals to 1. There you go. So this is the standard form, right? So all of the variables are grouped in one term instead of being scattered into multiple different terms. So that's step 1. So step 2 is we're going to obtain the 2D traces by setting one variable to 0, right? Draw the shapes out. So I'm gonna skip this step because I have these handy dandy diagram for me. And then I have listed, right? So if you have the xy trace, it's z equals 0, xz trace, y equals 0, and then yz trace is x equals 0. So this is the method I would recommend everybody to identify the surfaces without compromising speed and accuracy. In fact, this will give you much better accuracy than just hardwiring those equations to those names, to the corresponding names. So, so the first one is the xy trace. So we're gonna have x minus 1 squared minus y squared equals to 1. Right, this we're gonna have hyperbola, because look at that, we have x square, y square as well, but the signs are opposite, so that's how you know it's a hyperbola. Right, it's kind of like a circle, but just the signs are opposite. And then yz trace is x minus 1 squared plus 3 over 2 z squared equals to 1, right? So this is a circle, or sorry, hold on, never mind. Yeah, it is a circle, so, or ellipse in this case. So and then the yz trace is gonna be negative y squared plus 3 over 2 z square equals to 1. It's gonna be hyperbola again, right? Because we have y square, z square, but our signs are opposite. So why are we doing this? So that goes to step 3, right? Step 3, each trace is a side picture of the surface, and then we can match these traces to the corresponding surfaces. So what do I mean by that? So in this case, right, we have two side pictures are hyperbola, and then one is ellipse. So it's hyperboloid. Right? So, but is this one sheet hyperboloid of one sheet or two sheets? Right? So that's the next question. One sheet or two? Right? Because so the reason we can tell, one way to tell that is because all of the traces that we have created exist at the x, y, z, xz plane. Right? So since traces exist at, since all traces exist, how about that? Since all traces exist, right? X, Y, X, Z, Y, X, Z, Y, Z, Y, Z plane, right? So these are Z equals to 0, Y equals to 0, X equals to 0. That means the surface is continuous. Therefore, one sheet. Right? And you can take a look at the graphs of them, right? So for hyperboloids of one sheet, all traces will show up at the corresponding traces. But if it's two sheets, the x, in this case, the xy trace simply wouldn't exist, right? To find the traces, or in this case level curves, we have to set the z values to a constant k rather than 0. So because all of the traces exist, at x equals 0, y equals 0, z equals 0, the surface is continuous, therefore it's one sheet. Okay, so it's one hyperbola of one sheet. So the correct answer for this problem is gonna be D. Okay. Question number 3. Find the angle between velocity and acceleration at t equals to 1 for position vector at such. Right. So this one is kind of like a mix of lecture content that you have learned from multiple lectures, but because we have velocity and acceleration, right? So it's a motion in space problem, and then it's mixed with a little bit of basic vector identities. But anyway, so to solve this type of problems, we're always going to find the velocity and acceleration vector, right? The velocity is the first derivative of the position vector, and the acceleration is the second derivative. So r prime of t is going to be, so v of t, right, is going to be, r prime of t is going to be negative sine of t, right? I'm going to do these basic calculus skills really quickly to go through them, because I want you to focus on my solving methods rather than these numbers, because numbers are only valid for one question and one question only. But the solving steps you can utilize them for many problems. So cosine of t, you can check my math if you want, but I do believe they're correct. All right, so these are your acceleration and velocity vector. So once you obtain about them, right, so that's why I said it's a little bit mix of both, is that we're going, in this particular problem, we're going to take advantage of the basic properties of dot product. It's that we can rewrite the dot product as the product of magnitudes times the cosine of the angle. So if you rearrange them, you can get the angle between the vectors. So let's start with u dot v. So in this case, we're going to have r prime of t dotted with r double prime of t. So it's going to be sine t cosine t plus t minus sine of t cosine of t equals to t. Okay, and then r prime of t is going to be so negative sine of t squared plus t squared plus negative cosine t squared equals to t squared plus 1, because x squared plus y squared equals to 1. Same thing for r prime of t. It's going to be very similar. We're just going to copy and paste. Instead of negative sign, it's going to be positive sign. And then instead of t squared, it's going to be t1. So we're going to end up with square root of 2. Okay? So at t equals to 1, right? So the angle is going to be cosine of negative 1. And then we're going to have, so the dot product is going to be equals to 1, because t, value t at 1 is 1. And then we're going to plug in for the rest of them as well. We're going to have 1 plus 1 times root 2 equals to cosine of negative 1 over 2. So what do you ask? Like, what is the angle of cosine negative 1, cosine negative 1 and to the half? So I have a monkey brain, so whenever I try to find an angle, I always make sure I would draw this little cross like this. I'm sure your pre-calculus teacher taught you the same thing. So because cosine is adjacent versus hypotenuse, so adjacent is 1, right? And then the hypotenuse is 2. And then we have root 3 over here in case you're interested. So you can see that this is pi over 3, 60 degrees. So there you go. So that is the answer. Right? So this little triangle is always useful to help you avoid simple mistakes. So the answer is A. Question number 4. Compute the curvature at such at t equals to pi over 4, right? So I think everybody can agree that the keyword is the curvature here. That is telling you this is a curvature problem, right? The keywords curvature, r of t, and then at a particular time, and then is a curvature problem. So curvature problem is very simple, very straightforward. It's just quite a bit of math to do, but we'll get through them. So the first step is to find r prime of t and then find the magnitude of that. So r of t is equals to, I'm just going to copy it down, 2 sine t, 1, 2 cosine t. R prime of t equals to 2 cosine of t, 0, negative 2 sine t. So r prime of t, the magnitude of this is going to be 2. I think that's pretty straightforward. And then we're going to find the unit tangent vector, which is as the equation states, we're just going to divide the r prime of t by this magnitude. So t of t equals to 1/2, right? So that's 1 divided by the magnitude, multiplies this vector equals to cosine of t, 0, and then negative sine of t. So I'm just going to be a bit lazy, going through a little bit faster, right? So that's your unit tangent vector. Step 3 is we're going to continue utilizing our unit tangent vector. We're going to find the derivative of the unit tangent vector, and we're going to find the magnitude of that. So t prime of t equals to negative sine of t, 0, cosine of t, and then t prime of t equals to the magnitude of t prime of t equals to 1, right? Pretty straightforward. And then finally we can construct the curvature, which is kappa. It's just gonna be all the quantities that we have find ahead of time. So we have r prime of t right here under the new denominator, and we have the magnitude of t prime of t under the numerator. So kappa is just gonna be 1/2. Easy peasy. Answer is C. Question number 5. Find the length of curve of this curve from 0 to 2 pi. So this is length of the curve, right? So that's the keywords it's telling us is the length of curve problems. And then it's going to be an arc length problem. So for arc length problem, the first step is going to identify the r prime of t, but more importantly, the interval which the t belongs to. So r prime of t, rt is going to be sine t plus t cosine t plus t sine t. What a nasty equation. But here's the rule of thumb in Calc 3 exams. Whenever you see nasty things, as long as you're doing your math right and as long as you're using the correct approach, questions should be a lot simpler, not harder. Okay, if you run into some sort of mumbo jumbo that you don't see the end of it after solving for quite a while, chances are you're solving it wrong. That's just a sort of a sanity check for you doing in the middle of an exam. So the second step is to find r prime of t. So r prime of t equals to cosine of t minus cosine of t plus t sine of t, right? This is the product rule right here, and I'm going to apply the product rule again. Negative. This is just regular derivative, but it's gonna come up again, product rule, plus sine of t plus t cosine of t, right? So you can see that cosine t cancels out, sine t cancels out, right? Things gets nicer as you move along, as I've told you before, t sine of t, and then t cosine of t. Okay. So second step is we're going to find the magnitude of r prime of t. So r prime of t, the magnitude of that is going to be equals to t squared sine of square of t plus t squared cosine of t equals to t. Okay. And then finally we're gonna utilize the arc length equation, which is stated as such. So the inside is the magnitude of velocity vector or magnitude of r prime of t. Same thing. So L equals to 0 to 2 pi, right? As we have stated before, we have 0 to 2 pi is where our t belongs to. And then we have t dt equals to t squared over 2, 0 to 2 pi equals to 2 pi squared. Boom. Easy peasy. The answer is C. And then question number 6. A small metal ball is thrown vertically upward with the speed of as such, rises to a maximum height, and then falls, eventually striking the ground. How high does the ball rise measure from the point of release? And then they give you the gravitational acceleration is 9.8 meters per second squared. So again, we have these words like acceleration, velocity, or speed in this case, and you have some sort of height, right? These are words that are telling you it's some sort of motion in space problem, right? And I think this is a lot of words that's telling you, that's the type of problem. So motion in space, this is kind of like sort of a, we have talked about motion in space problems just a couple of questions before it, but this is more of a sort of full size motion in space problem. So for that, we usually start with acceleration vector, and then we're gonna integrate that acceleration vector to get the velocity vector. So I'm gonna start with defining my acceleration vector, right? So we have no information of the lateral direction acceleration, so we have no in the x direction, we have none in the y direction. But we do know the gravitational acceleration is 9.8 meters per second squared. And again, we remember it's pulling us downward. So it's negative 9.8, right? And then we're going to integrate this vector and then plus arbitrary constant. So v of t equals to integral of a of t, or I'll call this a of t dt plus C1 equals to 0, 0, negative 9.8 t plus C1. And then we're going to plug in initial condition and then solve for the arbitrary constant, right? The process is, if you think about it, the process is very similar to what we have learned in Calc 1 and Calc 3. So we're just applying this in a three-dimensional world. T equals to 0 equals to 0, 0, 19.6, right, at the initial throw of the object, right? It's 19.6 meters per second equals to, if we plug in 0, t equals to 0, we're gonna get 0, 0, 0, right, plus C1. So therefore, C1 equals to 0, 0, 19.6. So we have the full expression of v of t equals to 0, 0, negative 9.8 t plus 19.6. Okay. Step three, we're going to repeat this process again. We're going to integrate the velocity vector to get the position vector, which is going to be r of t equals to v of t dt plus c2 is going to be 0, 0, negative 4.9 t squared plus 19.6 t, forgot a t right there, plus c2. So we're gonna do this, and I'm gonna plug in the second initial condition, right? Or in this case, it's the initial position. Remember, notice that the time of initial conditions for the velocity and the position can be different. In this case, they just happens to be the same, which is r t equals to 0 again equals to 0, 0, 0. We're assuming it, it's thrown from the ground, so it's reasonable to assume that equals to, again, if we plug 0, 0, 0, t equals to 0 in, we're gonna get 0, 0, 0 plus c2. So therefore, c2 equals to 0, 0, 0. So the full expression of velocity of position vector equals to 0, 0, this expression, right? So, but we're not done yet, right? We have the initial position, but the question is asking us how high does the ball rise at the maximum height, right? So think about your physics, right? If the ball is thrown to the maximum height, right? So I'm call them at max height. At that instant of time, the ball is not moving, right? So that means the z component equals to 0, and that equals to the z component of velocity, which is right here, and then we can solve for t, which is equals to 2 seconds. Right, and then we can plug this t back into the position vector that we have right here. We're gonna get r of z, and then t equals to 2 equals to negative 4.9 2 square plus 19.62 equals to 19.6 meters. I'm ignoring the units just to make my solving process a bit faster, but that is how you get the answer of question number 6. Next question number 7. Assuming that limit exists, what is the value? So the key giveaway in this problem is this little limit sign, as we have discussed in my limits and continuity videos, if you want to check that out. And then, so they will tell you to evaluate some sort of limits. So therefore, you will have a notation of limit notations. So it's going to be a limit evaluation problem. So to solve a limit problem, the first step is always to plug in the point that you want to evaluate and check to see if the limit actually exists. Okay, so if a limit exists, then you don't have to do anything about it. It's just the value that you evaluated to. No need to perform the rest of the steps. But if you get 0 out of 0 or 0 over 0, infinity over infinity, that's a problem, right? Because that's an invalid, mathematical invalid way to get to a limit. So we're gonna solve that. Is gonna be limit x y approach to 0 0. We're gonna have of x and y, function of x y equals to, or sine of 0 is gonna be 0, and then the bottom is going to be 0, right? So it's a problem. So now it tells us that it tells us we should approach the problem with the rest of the steps. So step 2 is a big one, but it's divided into 2 sections. I'm gonna read it for you. I would say try to simplify the expression, right? I would divide limit problem generally in 2 cases. So if it's 2.1 or 2.2, right? So if it's a power fraction case, find and multiply the conjugate to simplify the denominator. That's what I would do for this type of problem. And if it's a trigonometric case, reduce the number of variable via quote-unquote U substitution. It's not the U substitution that you know of, and then we can use the L'Hopital rule. Okay, so in this case, by inspecting the function itself, we see a sine function right here. So that tells us it's a trigonometric case. If you want to get to know more about the power fraction case, you can go ahead and check out my limit and continuity videos. I demonstrate this approach as well, but in this problem, we are not going to use that. So it's a trigonometric case. Right? So we're going to use the U substitution. So it's not the same U substitution that you learned about in integration. We're just going to see if there's any commonalities in the what's inside the parentheses of the trigonometric function. So in this case, we can let U equals to x squared plus 2y squared. That means what's inside the sine function is going to be 4u. So, right? So f can be rewritten as sine of 4u over u. Let's drag this down, right? So that's pretty straightforward. So once we finish the substitution, we can plug in the point and then find the limit. So in this case, we're going to apply the L'Hopital rule as we have stated before. It's going to be limit of u approach 0 of the function equals to 4 times cosine of 4u over 1 equals to 4. Right. We're just gonna, what we did is just we differentiated the denominator and numerator together, and then we plug the u equals to 0 in. So the answer is 4. Not bad. All right, question number 8. It's a if function is defined as such, compute f(x,y) equal to 1. So so this is so the only keywords in this problem is this notation of partial derivatives. So right, it's a f(x,y) or in the Newtonian notation, it's the opposite, right? If it's x, y, so you differentiate as x first and then y second, and then it's x first, y second. It's written backwards for the Newtonian notation. These are the symbols of partial derivatives, so therefore it's a partial derivatives problem. So the first step is to find the first derivative, right? First level of derivatives. So we're gonna treat all other variables as constant, right? It's the same idea that you have learned in regular derivatives, but instead of those are just like some random symbols, now they are actual variables, but they are the same, right? Like we treat the symbol as constant, now we treat other variables as constant. We are only differentiating with respect to the variable of interest. So in this case, we're gonna have natural log, so it's gonna be x squared plus y to the fourth plus 2 to the negative first power, and then we're gonna use the chain rule, so we have 2x from the x squared, And then we're going to find the second layer of derivatives, whichever they are looking for. So in this case, it's going to be fxy equals to minus 1, 2x x squared plus y squared, or y fourth, plus 2 minus 2. And then, so the negative 1 is coming from the power rule. And then we're going to apply the chain rule again. In this case, it's relating to the y to the fourth. So we're going to have 4y cubic. And then we're going to plug in and evaluate as our final step. Fxy at 2, 1. That's where the point of interest from the problem, equals to negative 1, 2 times 2, 2 squared plus 1 to the fourth plus 2 minus 2 power times 4 plus 4 times 1 cubic equals to, this whole thing is 7. So this is 1 over 7. And then the rest, this is 1 over 49. This is 7. And then to the negative 2 power is going to be 1 over 49. And then the numerator is going to be negative 16. So we're going to have negative 16 over 49. Easy peasy. Answer choice is D. So question number 9. If function is given as such, then the direction of the steepest descent at 2, 3 is in the direction of the vector, right? So this is kind of a tricky problem in terms of identifying what it is, but the key word in this problem is actually here, steepest descent. So anytime that you see some sort of steepest, maximum, minimum, ascent, descent, and rate of change, that's all talking about gradients, right? It's talking about gradients of a function. So that's the type of problem, gradients of a function. So for these type of problems, we're going to always find the gradient of the function as defined as such. I hope you understand how to do them, right? Just a bunch of partial derivatives. So in this case, we're going to breeze through them. Fx equals to 1 times y exy, and then product rule, x times y squared exy equals to 1 y plus xy squared exy. And then we're going to do the same thing for fy. We're going to just go ahead and copy and paste and make some modifications. I hope you see that these things are quite similar, just changing some variables. Y, x squared, and then x, y, x squared. And then boom. So that's fy. So therefore, your gradient equals to fx, fy equals to, I'm just going to copy and paste, be a little bit lazy. Again, speeding up the process for you so the video doesn't take 3 hours to finish. So boom, there's your gradient. So to find the maximum rate of change, we can just simply go ahead and plug in a point of interest, which is 2, 3. Right here. But the question is asking for the steepest descent, right? So if it's the direction of the maximum rate of change, that is steepest ascent. So if you plug in, you're gonna get the steepest ascent. But in this case, we don't want that. We want the steepest descent. So we're gonna flip the sign once we plug in the value. So gradients of f at 2, 3 equals to, if you plug the numbers in, it's 3 plus 18 e to the 6th power. And then it's going to be 2 plus 12 e to the 6th power. So that is 21, 14 e to the 6th power. because it's asking for steepest descent, therefore it's going to be -21, -14, and then e to the 6. Boom. So if we want to find the value of maximum rate of change, sometimes the question will ask you that it's a scalar quantity. In that case, we can go ahead and find the magnitude of the function, but in this case, question is it's not asking for that, so there's no need to do it. But if we want the direction of the maximum rate of change, we can find the unit vector of the gradient function at that point, a gradient vector at that point. Or any scalar multiple of the unit vector also works because they're pointing in the same direction, just, scalar multiple each other, right? So in this case, we will divide what we found by 7 times e to the 6. We will get -3, -2. And that fits one of the answer choices, which is A. So, question number 10. Consider the function at r real number squared. Among its critical points, this function had something, right? So, this is an Extrema problem. I think everybody agrees with that, can see that, because, well, if you read the answer choices, it says a lot about maximum, minimum, right? These are Extrema quantities. So by reading the answer choices, you can figure that out. It's an Extrema problem, but we're not done yet because there are multiple types of Extrema problem. So is it a local Extrema? Is it maximum absolute Extrema? Right? So the key differentiation is this symbol, right? This denotes that x and y, the two variables, are defined on the whole real number axis. So that tells us because the variables are not bounded, have no constraints, defined on r squared, real number squared, that means it's a local Extrema problem. So therefore this is a maximum minimum problems, and it's a local Extrema problem. So the first step to solve this type of problem is we're going to find the first derivative fx and fy of the functions. So fx equals to y4 minus 1 minus x. Fy equals to 4xy cubic. Easy enough. So, and then we're going to find the critical points by using these two rules. It's fx and fy equals 0, or fx or fy does not exist. Okay, so these are the two criterions for a critical point. So in our case, fx equals to y4 minus 1 minus x equals to 0. That will give us x equals to y to the 4th minus 1. Right, we're just playing around with the same formula. And then for fy equals to 4x cubic, right? If we substitute this this equation in here, we're going to have 4y to the 4th power minus 1, and then y cubic, right? And this should also equal to 0 too. So by inspecting the terms inside these two terms, in order to get this equation equal to 0, y has either to equal to 1 or -1 from this part, from this term, right? So y equals to -1, 1, or it can be 0 from inspecting this term. So that's the potential. So these are the y values for the critical points, and their corresponding x coordinates can be found by plugging these values back in here. So we're going to end up with 0, 0, and then -1. So therefore, the CPs are 0, 1, 0, -1, and then -1, 0. And then second step is what we're going to do is we're going to find the second levels of partial derivatives, fxx, fy, fxy. So fxx equals to -1, fyy equals to 12xy to the square, right? We're just taking derivatives from here, and then fxy equals to 4y to the cubic minus 1 minus x. Never mind. It's not that. It's just 4 to the cubic. So once we obtain all of these informations, we're going to utilize the discriminant, right? D of xy. So we're symbol the D of xy, right? So this is another useful equations. I'm gonna highlight in red. So I'm not gonna write the whole thing down. Actually I will. So D of xy equals to well, this is gonna be -12xy squared minus 16 to the y to the 6th power. Don't be afraid of the huge power number, because we are only going to test them at the critical points. So for first critical point of 0, 1, so D of 0, 1 equals to, well, it doesn't really matter what value it is, but if we plug in zeros and ones right here, we're gonna get a negative number, 0, and then this is gonna be a negative number, so that's smaller than 0. Same thing for D of 0, -1, it's again smaller than 0, and then D of -1, 0 is equal to 0. So this huge block is the second derivatives for two variables. So you can read the whole analysis if you want, but I'm gonna just go ahead and jump straight to the conclusion right here, because the first one is smaller than 0, right? So it's a saddle point. It's a neither maximum or minima. Same thing for D at 0 and -1. So we have two saddle points. And then the last one is equal to 0. That means that the test is inconclusive. So if we go back to our answer choices here, right? We don't know if it's a maximum, minimum. Oh, by the way, if you see absolute extrema answer choices in the local extrema problems, go ahead and cross that out right away, because it's simply not true, right? And in a reverse way, that if it's absolute extrema problem and it has answer choices of local extrema, cross that out, right? It doesn't apply. And then we don't know, we don't have 4 critical points. We only have found 3. We don't have 2 local minimas. We don't know that. And then, but we do know is we definitely have 2 critical points, 2 saddle points, so therefore the correct answer is D. For question number 11, consider the function as such on the rectangular domain, and it's asking you to answer the questions about the function. So again, if we inspect the answer choices, we see a lot of terms about maximum, minimum. So this is, I think you can get the idea that this is an extrema problem. But again, is it absolute extrema problem or local extrema problem, right? So the key differentiation again is the constraint or bounds given or not. So in this case, the bounds is clearly given, right? So these are the constraints of the function. So that therefore is absolute extrema. So there you go. So it's absolute extrema because the constraint and bounds are given to us. So this one is a really long problem, so I have already written out the answers for you. So the first step is we can find the equations of the bounds, and I would highly recommend if you draw the region out whenever it's appropriate, whenever it's possible. So in this case, we have this rectangular region, and I have already labeled them as 1, 2, 3, 4. These 4 boundary lines because we're gonna use them later on. So the second step is we're going to find the partial derivatives and then find the critical points. Okay, find the critical points. So the function is rewritten is in the problem statement, and then we just took the partial derivatives. It's quite complicated. I'm not gonna go into the whole mathematical shenanigans, but they should be correct. So and then we're just going to find the critical points inside the boundary, right? So we set them equals to 0, and then we found that the critical points is 2, 2, but 2, 2 is somewhere around here. It's not inside our boundary, right? So we're not going to include that. So it's not in the boundary. We're not going to consider this as a critical point when we are doing our final comparison. So the step 4 is a little bit interesting because we're going to quote unquote sub the boundary lines into the function, right? To reduce the 2 variable function f, x, y to a single variable function containing x only or y only. So let's take a look at the first boundary line, this one. So on this boundary line, x equals to 2. It's fixed, right? It's fixed at x equals to 2, but y can be changing. So we're going to let the y be the same as it is. So x equals to 2, y equals to y, and then f becomes this. And let's take a look at another one. Let's take a look at the boundary number 3. So it's this top line right here. This case, y is fixed. Y is fixed to the constant value of 1, but x is free to move. Right? The boundary curve is spanning from left to right, so the x value is free to move. Y equals to 1, x equals x, we get this term. And then the rest is the similar idea, right? You can pause the videos whenever you want to verify my math is correct, but that's the gist of it. And then step 5, we're going to find the values of the functions on the boundary lines, particularly the critical points and the endpoints on the boundary lines. So because the expression of these terms are similar, again, I'm gonna just use one boundary curve to illustrate it as an example. So what I'm trying to do here is to try to find the critical points, right? Critical point occurs at the first derivative equals to 0 for a single variable function. But if you look at this expression is always greater than 0. So there's no critical point because, well, first derivative is never 0 or undefined. So there's no critical points, so we have to evaluate the function at endpoints. So this endpoints, right? If we go back to our curve, right? That's why this drawing is so helpful. So the endpoints is y equals to 1, and then y equals to -1, right? So that's why I have right here -1 and 1. So -1 we get root of 13, and then 1 we have root of 5. And you do the same thing for all of them. Again, the expressions are very similar to each other, but you just find that the endpoints. You find the critical points and find the endpoints on each boundary curve. So once you've collected all of them, right, it's a very long process, but this is the correct way to do it. No guessing, no second guesses, no, some sort of shortcuts to do it. This is the formal approach to solve this type of problems. Yes, sometimes question will be a bit easier, that you can take some shortcuts, but in case in situations where there is none, which is here, that you have to follow the formal process. So step 6 is going to be repeat the step 4 and 5 for each boundary line. So, but I have already collected everything here for you to take a glance. So let's go ahead and skip step 6 because I already finished it. So finally, we're going to collect all values of critical points and endpoints, and we can determine the absolute extrema. Again, the critical points inside the boundary, there's none, right? The only thing that we found is outside of the boundary. And then for each boundary line, right, we have 1, 2, 3, 4, right? Again, we have no critical points, but we do have endpoints. And then if you collected all of them, you will find root 5 is the absolute minimum, and then root 29 is the absolute maximum. So that is the correct answer to question number 11. So right here. So that is all for fall 2019 exam 1. So again, I would like to reiterate that this understand and memorize the solving process is much more important than the numbers that I just showed you, right? Because you can on an exam you can identify the question type using the keywords, and then you can apply the same solving steps for every single problems, and then without having to think about the definitions, derivations, and then you can apply the same solving process for every problem of the same type. So that's it for this video. Thank you very much for watching. I hope you liked it. I hope you learned something, and good luck to your exam, and I will see you in the future videos.